Welcome to Foster Physics. In today's video, we will explain horizontally launched projectiles, beginning with a 2D motion math translation worksheet. This worksheet is a combination of Cornell note-taking method and a reading/literacy strategy that I picked up along the way. We will begin working out our 2D motion problems by separating out our list of given information. We will begin by having one list of X variables and a separate list of Y variables. We will assume, in the same way that we made assumptions with our free fall gravity problems, we're going to still assume that the initial velocity is 0 meters per second and that the acceleration is due to gravity, since we're on Earth, is 9.8 meters per second squared. It will remain negative because it is a vector and it is describing the direction of the motion of the object. The next thing that we will try to figure out are the equations that will be necessary to solve the problems. In the X list, we have one equation that is appropriate. It is our displacement in the X equation, where it is equivalent to our velocity in the X times time. We only have one equation here because there are no initial or final velocities in the X. The velocity never changes. Therefore, we only have one. So that's why you will not see the notation of F for final, I for initial, or not for initial. With our Y direction, we have 4 different equations that can be used. And there's actually a 5th equation that we can derive when we're looking for time in certain situations. We will begin this problem by going directly into the example. The example here that we're looking at is pertaining to a ball being thrown horizontally at a speed of 40 meters per second. The cliff that the ball is rolled off of or thrown directly off of is 125 meters tall. How far away from the base of the cliff will the ball land? We have started with an image or a drawing of what the representation looks like. In this drawing, we can see a parabola-shaped trajectory for our projectile. The projectile is the object moving in 2 different dimensions, and that is our ball. As we start to observe the image that we have created, you can see that the velocity in the Y, it gets larger, while the velocity in the X stays the same. Our X list and our Y list has been created for us. However, we do know that there is an additional step that we need to add when we're dealing with horizontally launched projectiles. For this problem, what we want to do is go in and add a couple of more variables or a couple of more things to our given information. This is where we include our initial velocity in the Y, 0 meters per second squared, and our acceleration being due to gravity, since we're on Earth, as negative 9.8 meters per second squared. As we begin to work the problem out, we can use our given information in order to find an equation from our kinematic equations list that is appropriate. The most appropriate equation, based on us having a displacement in the Y, initial velocity in the Y, and an acceleration due to gravity, is displacement in the Y being equal to initial velocity in the Y times time plus 1/2 acceleration times time squared. If we choose this equation, we can go in and substitute out our given information for the variables in order to come up with time. One step that is very important to pay attention to is that when we get here and there's time squared being equivalent to 25.51, you have to be mindful that we still have to use inverse order of operations in order to get rid of or cancel out that square on the time. Once we go in and take the square root of both sides, we end up with time being equal to 5.051 seconds. I like to go in and show students an alternative to using that equation. What I choose to do, I choose to go in and take the equations at hand in order to derive another equation that may be a little bit easier for students. The equation that I like to derive comes from the same equation that we just used to work out the problem. So I like to go in and use that displacement in the y is equal to initial velocity in the y times time plus 1/2 at squared equation to come up with one that is straight to the point. Once we substitute in the initial velocity in the y for 0 meters per second, we can simplify this equation in order to get an equation that is a little bit cleaner. Once we substitute initial velocity in the y for 0, we end up doing away with this left-hand side of the equation. And since 0 meters per second times time is 0, we can just deal with the displacement in the y being equal to 1/2 times at squared. Since we are solving for time, we need to isolate this variable and manipulate the equation in a way where everything else goes to the other side. In order to do that, we do need to focus on using inverse order of operations. So I've divided 1/2 times acceleration on both sides. Once I have divided that from both sides, I'm left with 2 times displacement in the y over acceleration. Instead of keeping it as displacement in the y over 1/2 times acceleration, because we're dividing by 1/2, that's the equivalent to multiplying times 2. So we use the reciprocal in order to get the 1/2 from the denominator into a 2 in the numerator. This equation turns into t squared is equal to 2 displacement in the y over acceleration. To clean it up a little more, because we're only focused on time and not time squared, we have to go in and do inverse order of operations again in order to get rid of the square. When we take the square root of both sides of the equation, we're now left with time being equal to 2 times displacement in the y over acceleration, and we come back and take the square root of it all. Once we plug in our given information, which is our displacement in the y, which is negative 125 meters, and our acceleration being due to gravity on Earth is negative 9.8 meters per second squared, we're left with the square root of 25.51 seconds squared. In order to solve for time, we end up with an answer of 5.005 seconds. It is a very close to the answer that we did derive when we used our original equation. I want you to be able to go through and have options and choose the equation or the method that works the best for you. However, be mindful that the answers are very, very close. In moving forward with our question, we will look at the x side of the equation. The problem specifically asks for the displacement in the x. And when dealing with displacement, we had one equation. We also had one variable in the x, which was 40 meters per second. It was given in the problem. We now have a time. When dealing with projectile problems, the only thing that is common or shared from both the x-list and the y-list is time. It is one object moving in two dimensions, however, it happens at the same time. It doesn't matter if you chose the first route with our full out displacement equation to get 5.051 seconds, or if you use the derived equation that we derived from it to get the 5.05 seconds, we will still end up with an answer that is very close. With this equation, we did have to manipulate it a little bit. We had to divide both sides by time in order for us to have a velocity equation. So with the velocity in the x equation, if we set it up in this way, we can focus on solving for displacement. And the displacement is 202 meters.